Hello students, a very warm welcome to this session on Coulombs Law. In this lecture, we will be discussing about Coulombs Law. As you can understand, the word Coulomb is something to do with the units of charges. You got it correct. We are going to discuss something related to charges, that is the force of interaction between the charges known as electrostatic forces, which is what Coulombs Law describes. In this lecture, we will not only understand the equation, the theory behind Coulomb's law, but we'll also go through the history, the experiments that was conducted to prove Coulomb's law, and as well as the way it is theorized on the form of representation of Coulomb's law, and as well as we will be solving a couple of problems from your JEE Mains and JEE Advanced in this session. And this is quite an easy and an interesting topic, and questions have been asked several times from Coulomb's law. To give you a short introduction about myself, I am Muralidharan. I completed my MS in Electrical Engineering from one of the top ranking American university, and I'm also an IITian who completed BTech from IIT Guwahati, and I have filed several patent applications on state-of-the-art technology. So let's get into this interesting lecture. It's going to be super interesting, and let's get started with some history, which is a very important part of the Coulomb's law, and you would definitely love it as we get into the history part of Coulomb's law. And as you can see, in 1785, a physicist, actually a French physicist, Charles Augustin de Coulomb, published his three reports of electricity and magnetism, where he proposed Coulomb's law. And you know what? He was not the first person to propose Coulomb's law, or he was not the first person to understand the forces between charges. There were several people who have done it before. So it started something like this, around 400 AD or not. There was Thales of Miletus who came up with a theory around interaction between charges, etc. But exactly at the time, the charges were not known. Hence, he was proposing everything based on magnetic fields, etc. And it did not yield any useful results. And at the end of the day, it did not the theory or the kind of the observations that he proposed were not useful for doing any experiments in future or getting any applications as well. So it was not until 1600 1700 AD until Thomas Brown coined the term electric and electricity, when people started understanding the charges and etc., and people came up with the scientists came up with different theories around them, and people really started understanding this phenomena of charges. Okay, and during even when Charles Augustin de Coulomb was proposing Coulomb's law, parallelly there was Henry Cavendish, another physicist and scientist, working on similar thing. He as well theorized it, he as well wrote the papers, but he never published it. So the Charles Augustin de Coulomb's success lies behind this fact that he not only published his three reports in electricity and magnetism, and he also, his major success is because he published it. He as well as he proved it experimentally. He wrote a theory behind it. He kind of derived all the expressions. He proved it both quantitatively and qualitatively. So yes, of course, that is one of the major part around this entire proposing theory and proving facts. So this is where Coulomb's advantage was, and it was named after Coulomb's law. It's basically study of forces between the charges. And so let's get into this amazing theory. It's going to be super interesting, and let's see what kind of experiment was conducted so that he was able to prove this Coulomb's law. So it started something like this, and then he designed a Coulomb's torsion balance. And this Coulomb's torsion balance is nothing but it's a very interesting form of torsion balance. Torsion balance already existed. The beauty of Coulomb's was he designed it in such a way such that he could conduct experiments around electrostatic forces or the forces between the charges. So what does this torsion balance look like, and what are the major components and how we did it? Let's get into it and understand it. So there was in this torsion balance, there would be a silk fiber thread, and there would be a needle. And what happens is you will have on this needle you will have a ball, and this is going to be like an uncharged ball or sphere, right? And you will be having a charged ball or sphere on the other side. And then what would you do is you will suspend a charged object from outside. As you can see here, like a charged object, a similarly charged object was suspended during Coulombs law experiment, Coulombs torsion balance experiment. And then what would happen if they are both of the same charge, like charges? So like charges means both could be either positive, both could be either negative. In that cases, what would they do? They would repel each other, and similarly did repel, and this deflection, there was a theta deflection which was measured on the scale, right? And there would be some torque. The torque would correspond to some theta, and it would be some related to some like force, and that force was none other than our electrostatic force. Yes, he measured this electrostatic force quantitatively and he proved it experimentally, and this is one of the major reason behind Coulomb's success, apart from publishing the paper. And yes, exactly, and he made use of like charges because this repulsion could be measured in terms of angle of theta. He varied the distance between the charges. He even in he changed the charges of the spheres and experimented it. So he used torsion balance to measure the effects of the repulsive forces between two like charges, and based on this degrees of deflection he was able to prove the Coulomb's law. Okay, this is how it all evolved. That is very interesting experiment, and he specifically invented this kind of measuring instrument, or you call it whatever, like a lab equipment for proving electrostatic forces or the Coulomb's law. Okay, and this is what his observations were, or this is what he proposed. So he said that the forces are always along the line joining two charges. So wherever is the line is joining them, that is where the force lies. So the force acts along the line joining two charges, and he said that like charges, for an example, we have a positive charge, it could be either a negative negative pair or a positive positive pair. They repel each other, and as you can see, the force is directed away from each other. They are repelling each other since they are like charges. Okay, so this is about the first thing that you notice, that is the forces along the line joining two charges. And then he also said that like charges repel and unlike charges attract. Exactly. So here we can see there is a positive charge and there is a negative charge, and what is happening, this positive charge and negative charge forces are directed towards each other. That means they are trying to attract each other. Exactly. This is one of the most important postulates of Coulomb's law, and you should be understanding this really well. And then he proposed a very interesting thing, and he said that whatever is the force, it is dependent upon the magnitude of the charges. In fact, it is directly proportional to the magnitude of charges. So let's understand this thing. For an example, here we have this positive charge, and what are we doing is, let's say we have increased the value of Q1. Then what would happen? The force between them is going to increase as well. And let's take another scenario. In this scenario, what we are going to do is, we are going to reduce this value of Q2. Then what happens? The force of interaction between them also reduces. So he said that as I'm reducing, so imagine about one of those balls where he has been increasing the magnitude of charges, and then he observed that the force between them is as well increasing. And there was another scenario where actually it's the both forces in terms of magnitude is going to be the same. It's F1 to F21, just to indicate the direction. You'll understand that as we move into this lecture. But anyway, so what is happening here was, as he was increasing the value of charges or the magnitude of charges, the force between them was also increasing. And then he observed another interesting thing, same thing, like like he was reducing the magnitude of charges. Like one of these spheres over there, let's say it has been charged less, then the force was reducing, the force of interaction or the electrostatic force was reducing. So he found that the force is directly proportional to magnitude of charges. In fact, the force is directly proportional to product of magnitude of charges. So F is proportional to Q1 and Q2. And next comes the most important thing, or a very interesting thing as well. You must have seen this several times. So next thing he found was like there is an inverse relation between the force and the distance. So imagine that like the torsion balance, that if I am like varying the distance between the charges, then what is happening? The force is reducing. It is inversely proportional, but there is an inverse square proportionality between force and distance between the charges. So he found that there is an inverse relation between the force and distance between the charges. So let's say he must have done it either with numbers and finally come up with an equation, or plotted it on a graph. And let's say the force is plotted on the y-axis and the distance between the charges is plotted on the x-axis. Then in that case, what does this graph exactly indicate? This graph indicates y is inversely proportional to 1 by x square. This is kind of a graph that you must have come across earlier. If not, this is how y is inversely proportional to 1 by x square would look like. So exactly. So he found that the force is going to act along the line joining charges, and there is an inverse square relationship between the distance between the charges and the force. And then we also found out that a very interesting thing was it is like proportional to product of magnitude of charges, or the magnitude of charges. The electrostatic force is proportional to magnitude of charges. And there is another very interesting and an important thing that we should be understanding, that is like this electrostatic force is dependent upon medium. Unlike your gravitational force, if you remember your gravitational force is not so much dependent upon medium. It's not at all dependent upon medium, whereas your electrostatic force is dependent upon medium. So let's say you have two different mediums, one medium with some dielectric constant N1 and another medium with dielectric constant N2. And let's say that like the dielectric constant value of N1 is greater than that of N2. That is like like your force your force would be different for both of the medium. And let's say that N1 is greater than N2. In that case, N1 is like electrically more denser medium. In that case, what would be happening? The forces are going to reduce, or the interaction between the charges are going to reduce. And similarly, let's say you have N2 which is like less than N1. Okay, it's the same thing that we said earlier. And let's say in this case, what happens? In that case, you will observe you have changed the median from N1 to N2, where N2 is less than N1. Then you will observe that the force is increasing. Okay, generally we indicate this dielectric constant with K, but in this case we have changed it to N. The reason being, we'll be using this K as Coulomb's constant. So it was observed that electrostatic force is inversely proportional to dielectric constant. Okay, generally indicated with your K. Okay. And what do we know about this dielectric constant? We know that this dielectric constant is also called relative permittivity, relative electric permittivity. Okay, so relative electric permittivity or relative permittivity is how this thing is called. So more the relative permittivity, what would happen? Less would be the force of interaction between them. Less the relative permittivity, what would happen? More would be the interaction between them. And air as an electric permittivity, this also can be indicated with a symbol, like epsilon r. And air as electric permittivity of 1. Okay, that's it. That's all about the different kind of things on which electrostatic force is dependent upon. So as we understood, force is dependent upon the product of magnitude of charges and the distance between the charges and the medium of interaction. So we can say that force, that is electrostatic force, is equal to K into Q1 Q2 by R square. Okay, and what is this K is nothing but Coulomb's constant. It's not dielectric constant, it's Coulomb's constant, and we'll understand what is this value of K, etc. And yeah, and this is just, we are talking about absolute magnitude of forces. And yes, that is it. Yeah, this force is dependent upon product of magnitude of charges, and there is an inverse square relationship between the distance between the charges and the electrostatic force. And this K as a value 1 by 4 pi epsilon naught, which is, we generally use this as 9 into 10 to the power 9. Like generally it would be given in your books as 8.99, but for our examination purposes or problem solving purposes, we'll be not using 8.99 but rather 9 into 10 to the power 9. And the unit of Coulomb's constant is going to be Newton meter square per Coulomb square. Exactly, the constants will also have some units associated with them. Constants are not dimensionless. Okay, so K is equal to 1 by 4 pi epsilon naught, which is nothing but Coulomb's constant, and Coulomb's constant's unit is what? Newton meter square per Coulomb square. And when we are getting to the epsilon naught, so there is some epsilon naught. This epsilon naught is nothing but permittivity of free space. And what is the value of epsilon naught? 8.85 into 10 to the power minus 12, and the units is going to be Coulomb square per Newton meter square, exactly opposite of that of your Coulomb's constant, right? Because 4 pi does not have any dimensions, they are an inverse, direct inverse relation, hence that units would also be inverting. So we would be having a units of coulombs per Newton per meter square. Okay, and there are some limitations associated with this Coulombs law. Though a very interesting law, there were some limitations that was observed with Coulombs law, and these are the following limitations. And this is what this is where this Coulombs law is not applicable. Okay, for Coulombs law to be applicable, they should be like point charges, and or it should be spherical distribution of charges. Okay, either there should be point charges or spherical distribution of charges. So when we are claiming that it is a spherical distribution of charges, when it has some uniform charge distribution on its spherical surface, in that case we say that all the charges would appear like, let's say a Q charge is distributed on the surface. In that case, all the charges would appear as if they are concentrated at the center. So again, it becomes a case of point charges. So this is the major limitation of a Coulombs law, that it should be point charges or spherical distribution of charges. It cannot be a non-spherical distribution of charges or distributed charge body. Okay, and then it says that the charges should be stationary. Okay, we are dealing with electrostatics. In this case, the charges should be stationary, and the distance between the charges should be very large compared to the size of the point charges or the size of the charges as such. Okay, so if you have two charged spheres, the size should be significantly smaller than the distance between them, or else you keep it at such a large distance such that the size appears to be very small. Okay, so these are the three major limitations of Coulombs law. Okay, now we are talking about force. So force is not like a scalar quantity, it's a vector quantity. So in that case, it must have some direction. Okay, so whenever you are going to talk about it, or whenever you are getting this electrostatic force or any kind of force in mind, then you should be indicating or expressing it in terms of vectors. So this is what we said is the magnitude of force, right? This is the magnitude of force. Okay, this is the magnitude of electrostatic force. and you multiply with this r cap, which is nothing but the vector along the line joining the charges, right? And that comes out to be what? Your electrostatic force, vector quantity. Okay, and what is the value of the r cap depends upon like which kind of force we are talking about, or which force we are talking about. Exactly being said, whether we are talking about the force acting on charge q2 or the force acting on charge q1. Okay, so let's say we are trying to find out the force on charge q2, then what would we be doing? R cap is nothing but r2 minus r1, that is like final minus initial, divided by magnitude of r2 minus r1, basically r21 cap. Okay, so what is going to be F21? F21 is going to be K into Q1 Q2 divided by, right, this F21 is nothing but K into Q1 Q2 divided by R square into R21 cap. And F21, this is what we were discussing instead of R21 cap, right? So this is your R21 cap. We are still dealing with F21. So this is your R21 cap, but what you have to understand is it's final minus initial divided by the magnitude between them. There you would get that R cap vector, the vector, that unit vector along the line joining the forces. Okay, and that's it. We have expressed the electrostatic force as a vector quantity, which is a very important part of our understanding of forces or electrostatic force. And that being said, it could also be written like this. Instead of what was that r, what was the distance between them? Basically r1 minus r2. Okay, here we have written this r2 minus r1 vector. So on the denominator, what have we written? We have written something like r cube only. It's r cube only, r1 minus r2 whole cube. Okay, this is still an r vector, not an r cap. So finally you will be getting r cap divided by r square. Okay, that's it. And as you know, force is a vector quantity, hence what is true? F12 is not equal to F21. Okay, so we can't say F12 is equal to F21, rather they are of the opposite direction, exact opposite direction. They are of the same magnitude. Try and understand this thing. This is a very important thing. It does not matter what is the magnitude of this charge and this charge. Both of them can have different magnitude, but the force acting on one charge due to the other charge, like when we are just talking about two charges, then what is happening? The force magnitude is equal, but direction is not the same. Hence we can't say both this vector quantity, that is F12 and F21, are same, but rather they are of the opposite direction. Hence you would be directly indicating it with a minus sign. Okay, here we have that term, right? Yeah, exactly. So in this case, how is that r cap vector going to be? R cap vector is going to be like this. In this case, what is where is that r cap vector going to be? It's going to be in this direction, but it's all forces proportional to q1 q2 divided by the distance. None of them is changing, right? So that is all fine. That's it, and you multiply it with the Coulomb's constant. Okay, and now this might come to your mind. So what if I am making use of unlike charges? Yes, great, you have said how it works on like charges. Now what about unlike charges, where these charges are attracting each other? So how do we take care of this change in the force direction? So if you remember, in that case the force was in this direction. Now F12 is in this direction. So what should we be doing in this case? None other than just substituting the sign of the q2 as it is. That's it. If q2 value is given in negative, just write it down in negative, and let's say this is positive, just write down the magnitude in the force expression. that itself will reverse the direction, right? Once you multiply with the negative sign, let's say initially your r cap that you are calculating was in this direction, then what happens? R cap will turn out to be in this direction. Okay, quite easy. So F12 is equal to minus F21. That's it. It's really that simple, students. Okay, just substitute the sign, right? So for an example, Q2, let's say, is a positive thing, so minus Q2 would become a negative thing. So once I'm doing this, what is happening? I'm exactly reversing that R21 cap direction. Rest is the same. Okay, that's it. And yeah, this is how your final expression looks like. You can just take a note of it. That's all you need to understand. Quite a simple problem. Okay, that's it. That negative sign came from the like sign substitution. Okay, this negative sign, how did we get this? From the sign substitution that we just did. Okay, now let's get into really interesting problem that was asked several times. I mean, like several times, when the same kind of model problem was asked many times, not just in your JEE mains, but actually previously in your JEE advanced, then it was repeated in your JEE mains. Even now there are questions around them, little twisted questions. So very important thing. And you know what, in electrostatics generally you tend to get a question that is in a combination with mechanics, not such a very complicated a part of mechanics, but basic mechanics and basic electrostatic based questions you will get. Okay, so let's read the question and let's get into this question. It's a very easy, interesting, really kind of like the question that you want to do to understand electrostatic forces, and this question has been asked several times. So what does it say? There are two identical charged spheres and they are suspended by a string of equal lengths, and the strings make an angle of 30 degrees with each other. Then, so initially you had two charged spheres. Just imagine those two charged spheres, you left them free. Okay, none is bound. Then what happens? You will observe an angular separation between them that was found out to be 30 degrees. Okay, so they were hanging from the same point and with two strings of equal lengths, and it was 30 degrees. Then what you did is you immersed it in a liquid of density 0.8 gram per centimeter cube. So there must be some mass of the sphere. So what would be happening? It would be experiencing a buoyancy force, and it was observed that the angle remains the same. Okay, how is that possible? Because there is a buoyancy force. That means your gravitational force is reduced. And now what should happen? The upward component is reducing if you are trying to imagine it, and the horizontal component is also reducing. Why? Because this liquid has some dielectric constant associated with it, or it has a dielectric constant or an relative electric permittivity. So what has happened? Now we observe that the angle is remaining same because the reduced electric force is compensating the reduced total force in the vertical direction. Okay, actually its net force is going to be in this direction. Okay, and it is also given to us as that the density of the material is how much? 1.6 gram per centimeter cube of that solid sphere. Okay, so now let's do a thing. First of all, let's try and understand this interesting part, and before that let me quickly remind you. So let's say you have immersed it in a liquid. So this is the most important part. If you understand this, there is a standard method to solve this problem. First of all, let's understand this. You immersed it in a liquid with, let's say, dielectric constant K. Okay, then what happens? Let's say in air it was between those two charged spheres, if we say the force between them was like Fe. In air, the force between them, the electrostatic force between them was Fe. Now in that liquid, what it happens, it reduces by how much? Like by n. In this case we use k. We did not use k in that case because it gets messy and we tend to like kind of confuse it with the Coulomb's constant. Okay, that's it. So we'll be dealing with this, but there is a standard like steps to solve this problem, and we'll be understanding that steps. Once you understand that step, you'll be able to solve any problem of this. Okay, little bit of manipulations would be required. So we'll be starting with case 1. Okay, case 1 is in air, right? Okay, and what do we have in air? So we have this like angular separation between the strings to be 30 degrees, that is given to us, and theta is going to be like half angle of that angular separation. Let's keep it as theta itself. We need not substitute it as, or we need not reduce it to 15 degrees. That's not necessary. So if this is theta, if I'm going to draw a line like this, what you're seeing over here, this is also going to be theta. And what would be the tension force be? Like we are taking it to be T, and how it would be acting along this string. Now if I'm going to resolve this component, one component is going to be like this, which is going to be what? T of cos of theta. And along the horizontal direction, right, another component has to be there, right? And that another component is what? T of sine of theta. Okay, I'll be labeling this as Fe, and this should also be Fe in terms of your magnitude. And before we dive into this problem, let's understand one thing. I'm going to define a quantity Fe. What is the value of Fe? Fe's value is Coulomb's constant. This is not dielectric constant, but Coulomb's constant into Q1, Q2, but actually they are all similar charges. Instead of Q1, Q2, can I directly write it down as Q square, right, divided by R square, or in this case let's keep it as D square. Let's say the distance between them is D square, sorry, D, my mistake. Okay, it's D, so we'll be calling this as D square. Okay, simple. Now what we need to do, simply we need to balance the forces. Really simple. First of all, let's work around T sine theta. We know, write down the first equation. It says T sine of theta is going to be how much? F of E. Second one is what? Second one says T cos theta. It's basically balancing the weight of this spherical ball. Okay, still in air. So what would we be getting? T cos of theta should be equal to mg. Okay, now let's understand one more important thing around this. So we know something like this, that Fg, that is like the weight, is what mg, which is nothing but, if I'm going to express this mass, okay, how do we express this mass? In terms of density of that solid, right, of that sphere into volume. Density is going to be what? Mass by volume. Now we are writing down mass is equal to density into volume, so we can write it down as something like like density of the solid into volume into G. Okay, and that is going to be how much? Students, it's really simple. This has to be rho S into V into G. Okay, now from case 1 we can do a thing. We can simply derive an expression which says that tan theta is equal to Fe divided by that whatever we derived just now, which is nothing but you know rho s into Vg. Okay, so what we are going to do is, from case 1 we know this thing, tan of theta is equal to what? Can we say something like tension into sine of theta, that of tension into cos of theta, which is nothing but 1 divided by 2, isn't it? It's nothing but 1 divided by 2. Okay, that's it. You have this t of cos of theta in this direction, and t of sine of theta in this direction, and this is going to be Fe. This is that rho s into V into G. So let's do a thing. Let's substitute the value of your 1 and 2. So we'll be getting something like, if you remember from the last expression, 1 was what? Fe. You're not going to write down the whole value unless required. This is what we are supposed to do with each and every problem. And then the 2 is going to be what? Rho of solid into volume into G. Okay, now just keep it aside. This is what? 1. Okay, now we have the second situation. What is that second situation, or case 2? Case 2 is immersed in liquid. Okay, now comes the most interesting part. Okay, now the thing is, when immersed in liquid, what is happening? When immersed in liquid, actually it's going to also experience not only reduction in the electrostatic force, but also something like a buoyancy force. So there is a medium, right? If there is a medium, what is going to happen? There is a liquid medium, so this is going to give a buoyancy force in this direction, Fb. And what is the value of Fb? Fb is the density into volume displaced by the solid into G. Okay, density of the liquid, whatever is the density of this liquid, let's say this liquid as a density rho L, into volume of the sphere, whatever is the volume of the sphere, into G. And in this direction, what it is going to be? It is going to be mg as usual. We'll be having an mg as usual, which is nothing but, we wrote it down to be something like rho s into V into G. Okay, we'll be writing it down directly. And what is that balancing component? Balancing component is going to be that same thing. Okay, this is tension. What is this balancing component going to be? This is the theta. This should be what? This should be T of, sorry, my mistake, cos of theta, right? Sin theta is going to be the other one, if you remember. T of cos of theta. Okay, right? Because this is T of cos of theta, and T of sin of theta is going to be in this direction. Now, need to understand also one more important thing. What is that important thing? See, now the interaction between these charges is also influenced by this liquid. Okay, let's say if it was Fe in air, how much, let's say this liquid has not only the density of rho L, like mass density of rho L, but it has something like a dielectric constant of K. Then in that case, what happens? If initially in air, if this force was like Fe, it would become what? Fe by K. Okay. If in air it was Fe, it would become what? Fe by K. Okay. Really simple. Again, same old equations. We start with equation number 1, which is nothing but T of sine of theta, which is going to be how much? Like Fe, if it was an air, it's K into Q square by D square. There we call that to be like what? Fe, right? But now we need to divide it with a K, dielectric constant. And then we have T of cos of theta. Now the T of cos of theta is also reduced. Which are those two balancing forces? Mg, is that it? So Mg we can write it down as rho of solid into volume into G. And what is the buoyancy force? We know that rho of liquid into volume into. Okay. So yeah, now again we are going to do 1 by 2. To say that what is 1 by 2 again? Sin theta divided by cos theta, which is nothing but tan theta. Okay. So we can say from 1 and 2 again. What do we have? We have something like tan of theta is equal to T of tension times sin theta component divided by tension times cos theta component is equal to how much? Sin theta is now Fe by K, and what was your T cos theta? See, here we have rho s into volume into G minus of rho L into volume into G, right? Let's write it down that way. Rho s into volume into G minus rho L into volume into G. Okay, what are we going to do? A small change. We have to bring in a small change just for the convenience of calculation, no other reason. We are going to say this is nothing but rho s minus rho L into that of V into G. Now finally we can write down the expression something like this. Okay, it should be Fe by K divided by rho s minus rho L into that of volume into G. Okay, that's it. So we can, if you understood a very interesting thing, what can we do now? We can do a very interesting thing, that is say that if I'm going to call this like 2, then you can say that 1 is equal to 2. Both are tan theta, isn't it? Yes. So we can say that from 1 and 2, tan of theta is equal to how much? Fe divided by density of that solid into volume into G is equal to how much? Like Fe by K divided by rho S minus rho L into volume into G. Okay. Now we have this expression. So what are we supposed to do? We're supposed to solve this expression to find out our final result. Okay, these are like the standard steps and procedures that needs to be followed. But here we will be also understanding the effect of medium. Hence we have this question now. So I'm just cancelling it out just when I'm equating this both. Okay, right? So this comes out to be how much? This comes out to be from both of this simplification. If I am going to reduce this equation, we'll be getting 1 by rho S is equal to 1 by K. What is that K? Dielectric constant into that of 1 by rho S minus rho L. Okay. Now, can we say that K is equal to rho S divided by rho S minus rho L? If I'm going to take this K on the other side and this rho S on the other side, can we say that K is equal to rho S divided by rho S minus rho L? Okay. So we can say K is equal to rho S divided by rho S minus of rho L. Okay, and what all do we have? We have the value of rho S and rho L. Okay, how much is rho of liquid given to us? Something like 0.8 grams centimeter cube. Let's keep it as 0.8 because both of them do have same units and we are dealing with ratio in this case. And what is given to us as rho S? Rho S is given to us as 1.6. Okay, and what do we need in the denominator? We need rho S minus rho L. Rho S minus rho L is how much? Like 0.8. Right, 1.6 minus 0.8, it's going to be 0.8. Okay, what do we have over here? Rho S value, rho of solid is 1.6. Rho S minus rho L, we know it is how much? It is 0.8. What do we get this to be? Like 2. Yes. So what is the value of a dielectric constant? Dielectric constant value is going to be 2. The force of interaction between them has reduced by half. The electrostatic force of interaction between them has reduced by half. That's it. Really simple, really interesting. Yes, very popular kind of question. I hope you understood the effects of medium. Now let's get into another interesting problem, a JEE advanced problem. This will give you a perfect understanding of fields as well. I know we haven't started with fields, but this will give you a good understanding, and post that it will be quite easy to even deal with fields. Okay, just try to focus on the concept. It's a very, very simple concept. So a few electric lines for a system of charges like Q1 and Q2 are given to you, and these lines suggest something that we will get into that later on. But here what are the given options to us? That Q1 is greater than Q2, and the second option should have been like Q2 is greater than Q1, and then at a finite distance to the left of Q1 the electric field is 0, or at a finite distance to the right of like Q2 the electric field is going to be 0. Okay. First of all, let's dive into this problem and understand this. See, we have like 3 different kind of lines of electric field. But if we are observing the lines between them, that's not useful for our conclusion. Why? What is the reason? Because they are just interaction lines. Same, both charges would have some the same amount of lines leaving them and entering them. So it's basically describing the force between both of these charges. Now coming to the other one, if you are observing Q2, how many lines are there? like two lines are present, right? There are like two lines on this side, and on this side how many lines are leaving the charge q1? More number of lines, okay, more number of lines. And how much are they? 6, right? You're on the sixth one, so 6 lines. That means if there are 6 lines on this side and 2 lines on this side, whose magnitude is greater? Whichever has more field lines exiting from them. In this case, in one case it's entering, in the other case it's exiting. Basically that's how they are able to have this line. But whichever has more field lines entering or exiting from them would have more magnitude of charges. So we know that now q1 magnitude is greater than that of q2. Okay, we have our first conclusion. We got probably one answer, but it's a multiple correct problem. Now let's understand this thing, a very very important thing. So what is actually a field? Okay, to give you a quick explanation, you would be placing like a test charge either on this side or this side, and you'll be measuring the forces due to individual charges on them. So it is being said that in one of the cases, it's either to the left of q1 or to the right of q2, the field is going to be 0. We are supposed to assess this force on the test charge. Okay, so let's assess the force on the test charge. If this test charge is at a distance, let's say x from q1, and the distance between these charges, that is q1 and q2, is t. Okay, so what would we be having? Total force or the net force to be something like k into q1 into q0 divided by x square. That is going to be like a repulsive force. Okay, we are just discussing about this side. Later on we'll move on to the next side. First of all, let's understand if it's feasible on this side. And on the other side, let's keep it as negative, not necessary, but the forces are going to act in the opposite direction. This is a negative charge because field lines are entering them, right? So it's going to be negative charge, so that would be like an attractive force. Distance between the test charge or the point charge is what? D plus of x. There is a distance d over here and x over here, so it's going to be d plus of x whole square. So do observe a thing here. What is the thing that we need to observe very carefully? That this term can never become 0. Why? Because whatever you are subtracting from q1 by x square, right, is always going to be greater than q2 by d plus of x square. Why? First of all, we know that your q1 magnitude is greater than q2 magnitude. Now what have you done? You have divided that q2 with a larger quantity. That means q2 by d plus x square is going to be further lesser than q1 by x square. Okay, it's really that simple. That's it. Okay, hence this can never be 0. Now let's analyze the other case. Very simple. So let's say I'm going to analyze the other case, which is like a distance y. In this case, let's say this test charge is placed at a distance y to the right of q2. Then in that case, what is the net force going to be? Let's call this as f dash. That is going to be like k into q1, right, into q1 into q0, which is this test charge, right? We are discussing about this test charge. Just forget this test charge. Now this test charge does not exist. We know this case is not valid. Divided by d plus of x, right? This distance d, sorry, my mistake, d plus of y whole square. And then we would have minus k into q2 into q naught divided by y square. So if we are going to analyze this case, this is like q1 divided by d plus of y whole square, and this is what q2 divided by y square. It is quite possible that k into q naught is common, right? It is quite possible that at some point, really point that is very close to q2, what is happening, like your value of q2 by y square is greater than that of q1 by d plus y square, because you are dividing it with a larger value, right? Here this is larger value and here this is what, a smaller value. Okay, but we also know that other condition, that q1 is greater than q2. So there could be ideally a point where this would become a 0, and there would be ideally a point where this would become 0. Hence, to the right, that is this side only, we could have that solution. To the right of q2 we can have that solution. Okay, so our answers would be A, it's a multiple correct choice thing, and at a finite distance to the right of q2, there we would be having it. So we'll be understanding more about this field, more about electrostatics in the upcoming lecture. I hope you like this video and you enjoyed this concept. And yes, keep working around electrostatics. It's a very interesting and an important topic. And yeah, take care. See you in the next class, students.